All right, guys. So first lecture on probability. Let's begin with a seemingly strange and boring question. You heard it many times. You take a coin, right? And you toss this coin. What's the probability that the coin lands on heads or lands heads? And of course, what's the meaning of your answer? So a lot of you say 1/2, but would anybody care to tell me what does this mean? So somebody asks you.
One half means that there are two possibilities. So you're going to get one out of two possibilities each time you try your coin flip.
Thank you so much. That's a very, very nice first description of it. There are two possibilities, right? We're assuming that when you toss a coin, either it's heads or it's tails. But there is a possible danger here, guys. You are either going to live to be 1,000 years old, or you're not going to live to be 1,000 years old. Also two possibilities. Would you say that the probability that you live to 1,000 years old is 1/2?
Nope.
But there are still two possibilities. You agree? You either live or you don't. Well, I would say that the third possibility is that you are living dead, and that's really true for 80% of the people. So it's you're neither living nor dead. But if you drop that situation out, then there are only two possibilities. Yes.
They're not necessarily equally likely. You don't know enough about this.
Yes, they're not necessarily equally likely, and you should always remember, guys, it's going to be very dangerous, and at times you might make that mistake that you forget that there is no symmetry, that they are not equally likely. So then what do we mean? That when we toss a coin, the probability is 1/2. Right? Specifically, as in terms of an experiment or some description, that it's very clear what is meant, that the probability is 1/2. If we can answer that, then we might begin to understand how to think of probability and what it means.
So like half of the times you run the test, you'll expect that result.
Okay, that's a bit better, but of course, half of how many times, right? So here is what we can imagine. In fact, that's what we're doing. And when I was writing it, I actually threw coins many times, right? So what we can do, guys, we have this idea that let's do the experiment 20 times. This is doing the experiment first round, means I toss the coin 20 times once and see what happens, right? I'm tracing how many times I have heads divided by total many trials. Okay, and you can see that green is heads, red is tails. Yes. So first I got heads, so it's 1 out of 1. You see, I had only one trial so far. Then I throw the coin again and I get tails, and so now I have 1 out of 2 trials. Then I throw again, I have again tails, 1 out of 3 trials, right? And onwards. And by the 20th trial, I have accrued 20 attempts, 20 tosses, and out of them 8 were successful. 8 of them gave me the heads on the coin. Yes. So 8. So do you see, guys, that here you're envisioning NH divided by N? You are seeing that there is a sequence. You see, first term of the sequence, second, third, 20th term. We have a sequence. Just like before, we have a sequence. So well, we're going to get to probability in 1 second, and we'll see what happens. So this is one sequence, but you can see in trial 2 that the sequence is that's good. I like that you mentioned what you do. But run 2, guys, the sequence is entirely different. You see, it's a non-deterministic sequence because every time you repeat it, you're not producing the same outputs, right? So for instance, when you're dealing with the sequence 1 over n, your first outcome is 1 over 1, second is 1 over 2, 1 over 3, 1 over 4, right? But here, the outcomes are not the same. You can see that, let's say a 3. Here we have 1/3, here we have 2/3. You see that the sequence is non-deterministic. Yes, and here I run it 20 times for both situations, and here I got exactly half, and here I got less than a half. And you can see, by the way, it's pretty interesting how many times I had tails. A lot of people, when they try to fake randomness, they tend to shorten the number of heads. They think, oh, I had too many heads, and now I have to switch to tails. But what actually happens is that through randomness, you have a very long sequence. Here you have like 9 successive tails in one case, right? So very long successive heads or very long successive tails are very common when you actually have true randomness. And usually people get scared, they switch more like heads, tails, heads, tails, heads, tails. And that is right away indicative that somebody was not doing anything randomly. It's very, very difficult for a person to be very random. Good. So this is that situation, guys. And in fact, let's look at the simulation. So here is the, I actually threw coins, but here is the simulation. Let's see what happens when I toss 10 heads. See, I got 0.6. In other words, total heads divided by trials is 6/10. Yes. And now if I clear this result and I repeat it, I will get possibly a different outcome. Here I have exactly half and half. Yes. So it's always a different outcome if I toss 10 times. Now let's see what happens if I toss. There's some variability. Now I toss 100 times. You see, I tossed 100 times and I got exactly 1/2. It claims. I toss again 100 times, and what do I get? And I get 0.6, 0.4, still some variability, right? Now let me toss 1,000 times. I will still have variability, but do you see, guys, that it begins to be less noticeable? The variability, it begins to disappear. It looks very much like 1/2. Do you agree? 0.493 begins to look like 1/2. Let's try again. And that again, you see, it looks pretty much like 1/2. And if I do it 10,000 times, it will look even more like 1/2. Okay, guys? So what we have here is we have this sense that there will be convergence. We'll actually later in the course, hopefully we'll talk more about how and when to expect convergence. How many tosses should you have to have a convergence to within a certain error bound? You understand? There is an error, you agree? So I don't get exactly 1/2, but what I'm getting, the probability it appears, is the convergent value. In other words, the philosophy here is rather complicated. That's why probability is very complicated to grasp. The philosophy here I drew a table. You can see I did it 5 times. With 10, you can see the variability with 10. If the variability is, let's say, smallest I got is 0.5, largest I got is 0.8. Variability is 3/10, right? So there is an error of 3/10 within the trials I got. Now, if you look at the 100, at the row representing 100 trials, you can see that the variability is significantly less. You agree? Variability is maybe, what is it? The biggest I got is this, the smallest is this. So roughly 0.2, 2/10, right? It decreased here, right? And here for 1,000, it's even smaller. And for 10,000, it's much smaller. You see? So this suggests that if you begin to look at this, at the rows, let's say from the 10,000 row onwards, you will begin to see something that's indistinguishable from 1/2, right? And of course, the error, in other words, the error that makes it different from 1/2 is disappearing. Yes? So probability is, in some sense, the limit of this running sequence. Okay, limit as n goes to infinity of the number of successful trials divided by total number of trials. So in this situation, the individual outcomes are not determined, but the end is determined. The end behavior is determined. All roads lead to Rome. So I'm not sure how you're walking, but you end up in Rome. Yeah, that's kind of what's the idea. And philosophically, you think that nature has a preference, and if you give nature enough time to display that preference, you will see it. right? So in the limiting behavior that you're seeing nature's preference. So nature has no preference for the coin landing on heads or tails. That's why you should see that the ratio is 1/2. You understand? Because if you have a lot of no preference, egalitarian means you gave a lot of trials for nature, and then half of those trials, more or less, should be heads, and half of them should be tails. You follow? So probability 1/2, that means that there is no preference. So here is a small example of how you might calculate it, guys. So you are betting on boxer A to win against boxer B, because boxer A is twice as good as a fighter compared to boxer B. What's the probability that you win the bet? So twice as good, guys. Here I assume I know nature's preference. What does it mean twice as good? It means that if those boxers were to fight infinitely many matches, twice the number of matches will be won by boxer A as by boxer B. Let's say we're assuming that that they cannot have, what do you call it? They cannot have a draw. Good. So the answer is, if I take this limit, guys, when n is large, the number of successes for A is twice the number of successes of B. And n is just consistent of number of successes for A plus number of successes for B. So it's 2 number of successes for B divided by 2 number of successes of B plus number of successes of B. And here I can clear this number out. I can cancel NB, and I get that the probability should be 2/3. You still had only 2 outcomes here, right? Either boxer A wins or he loses, but the probability that he wins is 2/3. Because nature prefers one outcome to another. Good? And here is, I wanted to play you that song, but I'm sure you are not aware of it. How many of you know the song by ABBA, The Winner Takes It All? Do you know it? And don't be embarrassed. My God, you don't know it. And I do not know. I can try playing it for you guys, but I think Zoom decided to make lectures less fun by posting an update, at least on my end, which makes streaming very choppy, or the sound doesn't go through, I think, right? I think I had these problems. I didn't have them before, but I started having them. Please no ABBA. You remind me of Israelis, right? They had this. You have those cool people, and they said the only way to torture them is to play ABBA. You know, that's the only way to get them to crack.
I grew up in the 1970s and only weirdos liked ABBA. Sorry.
Yes, well, so okay, so you don't want ABBA, fine with me, but we do want to understand this one phrase, if I heard it correctly: the gods may throw the dice, their minds as cold as ice, and someone way down here loses someone dear. Now, what do they mean, guys? Their minds as cold as ice. So that means when you throw a dice, they are indifferent to your fate. You agree? They are indifferent to your fate, which means that the die has 6 outcomes, and each outcome is just as likely as any other outcome. Do you agree? By the way, I just noticed we have 2 bearded sages in this class. So you see how interesting. Right. So here is that situation. So let's say, what's the probability that the die comes up with the number 1, right? Displaying the number 1 on it. So it's n of 1 divided by n. And you can see that N is just the total number of outcomes, 1, 2, 3, 4, and they are all the same. Do you agree? If N is very large, if nature threw the dice many, many times, ad infinitum ideally, then you will see that those numbers will be matching. They will be essentially the same number. So that means that what I have is N1 divided by 6 N1, and I can cross away N1, and I get the probability is 1 over 6. Do you see? 1 over 6 means weighing, or well, I mean, everything is weighed the same. Everything is the same, no matter, no preference. So the worst I mentioned, I'm not sure if you care about it, but let's say if you want to know, let's say you're asking a girl on a date and you want to know the probability that she would say yes, the worst probability is 1/2. Because if the probability that she says yes is 1/2, she is indifferent to you. Right? That's the thing. All right, guys. And then the next question. If the probability of an event is 0, does this mean the event cannot happen? Right? So that's another thing. Maybe you watch Dumb and Dumber. Right? I remember this guy is coming to a model and he's saying, will you date me? What's the chances of you dating me? She says 1 in a million, and he gets very excited. Right? Now, if the probability is 0, does it mean it doesn't happen?
I would say yes, as in there's 0% chance that my right hand will become my left hand. Not going to happen.
That's interesting. You can take a mirror and it will become, right away. So what do you think, guys? One person said very confidently. What about you? Probability is 0. Does this mean the situation never happens?
I also think that the answer is no, because it's not possible to have 0 probability.
Wait, no, I meant like the answer is like no, just because it's 0 doesn't mean the event can't happen. So like, yes, if the probability is 0, it can still happen. I just don't know why.
But you say it can still happen, but you do not know why, right?
Yeah, I don't know why.
Okay. But you're mathematicians, guys, you should have a good sense of it, right? And that's one thing that's so interesting about probability, and about, by the way, how it relates to today's situation. There are so many interesting things I could show you, if of course you cared about, right? There is one guy in Germany who made an analysis of mortality and other factors about what happened in Germany, and made a claim that in the data he cannot show that there is a pandemic. And it's a very interesting video. It's in German, right? I think you can try to play subtitles. I mean, YouTube translates it automatically. But yeah, I'm not sure if the translation will be good. I haven't checked those things yet, right? But I can show you the main argument if anybody is interested. I can very quickly explain what this guy is saying and how is he making that claim. And a bunch of people say it's nonsense. There was this guy that was debunking his video, and I look at the debunking, and and the interesting thing about probability is that two people that are using correct information can arrive, everything that they're saying is correct mathematically, but they arrive at opposite conclusions, because this thing is just always difficult to interpret. Understand? So you have correct data, but how do you interpret it could be entirely different. What you look, what you say, and whatnot. So that's the beginning of it, right? We ask, something has probability equal to 0. Does this mean that it never happens? And the answer is, of course, obviously not. I mean, I hate things that are, I always like to say wrong, or put things upside down. So here is one example, guys, of probability being equal to 0, and it still happens. Now, how many of you order food with Uber or some other DoorDash or something like that, right? You order food and you have a delivery person come and bring the food to you, right? Now, let me show you that the probability that he brings the food at the time that, at the time that this device is displaying is 0, right? So here is the situation. Imagine you schedule a delivery and the delivery will arrive between 12 and 1 o'clock, which we can normalize to be between 0 and 1. You agree? Between 0 and 1. And let's say that there is no preference on time. You agree that, in other words, between 0 and 1, any time is equally likely. So what does it mean to be equally likely? It means that if I divide this interval time into, let's say, 10 intervals, then each interval has 1/10. You understand that if you simulate the delivery arriving in this time, within each interval, the arrival is 1 out of 10. If I divide the interval into 100 pieces, each piece is equally likely as any other piece of time. Each 100th segment of a time is equally likely to occur as any other segment of time. You follow what I mean? In other words, in each of those segments of time, the delivery person is equally likely to bring the delivery package. So the probability, if I divide it into n segments, the probability that delivery comes between k and k plus 1 moment of time is 1 out of n. Are you with me? Because divide the time into n parts, the probability is there. So the probability that and of course the particular moment of time t0 that you're looking at is always in one of those intervals. So as you divide those intervals, you see that the probability that the arrival is specifically at the time is 0. Do you follow? The specific time t0. So in other words, what's the probability that your package arrives exactly at 12:30? It's 0. You understand? Because divide this interval, you see that the probability is lower than any positive number, which makes it 0. Do you agree? Must be that you understand this question, guys. Yes? The probability there is 0. So the probability that here is what I want you to understand, guys. What's the probability the delivery arrives at 12:30? 0. What's the probability it arrives at 12:15? 0. What's the probability it arrives at any other time? 0. So how do you get the package? Right? At any moment, just focus on any moment in this interval. At any of those moments, the probability of package coming is 0. So how do you get the package? Do you agree with my argument? You should better agree with my argument because it's infallible. It's absolutely correct. So how do you get the package?
This looks like the Xenos paradox argument.
Well, I mean, perhaps there is a maybe aftertaste of it. No takers?
I mean, like you're dividing the subintervals into like infinitely small, but like it's gonna take like 1 second or something for you to like take the package. So
well, but let's say the second there is a beginning, right? Suppose that there is a beginning where the package begins arriving. I'm not sure if it's easy to define, but there is a beginning, right? There's a ring, like let's say the moment when your phone zaps and something begins to appear. You might argue this way that there is essentially no beginning or end to things. It's not. Some of them are fuzzy, right? It's not quite clear when something begins and when something ends. But you can also say entirely differently. You can say this. You see, guys, that we describe probability as a sequence. Right? In terms of simulation, imagine that there is a moment, a definite moment in time where the package arrives. Imagine you do the simulation, and you do the sequence of simulation, and success is when the package arrives at that very moment of time. If you do the simulation again and again and again, what you see is that success happens 1 through infinity. You understand? So in other words, it happens, but then the limit is 0, because imagine that successes of heads divided by total, right? There is always a repetition of heads. Do you agree? if you run the experiment again and again, you will see more heads coming. Correct? It would not be like that heads appeared once and then never again. But here, when the delivery person brings you the package, if you could simulate, if you could repeat this entire thing again, the next time the delivery comes will never be the same moment of time. It will never repeat. Or it will repeat with such low frequency that the limit will be zero. The limit of successes divided by total number of trials, it's a running frequency. Do you remember? The ratio does not have to be zero for the limit to be zero. So you could actually have success and then the success does not repeat. Okay, so what you witness when a package arrives, you witness a miracle. And you witness miracles all the time, guys. My definition of a miracle, write to yourself. Now you can mathematically define what a miracle is. A miracle is an event that has zero probability chance of occurring. A chance of zero of occurring, and miracles occur all the time, every day, every moment, without stop. Every second, right? That I'm talking about something today, this very moment, use those particular amazing words or very horrible words that I use, it's a miracle. Never to repeat. So probability of zero can happen, and there is nothing so mysterious about it. Because probability, guys, is not to say something cannot happen or can happen, it's only to measure that something happens with extreme infrequency. Right? If the probability is 1 in a million, then it's not frequent, but it happens with some repeated frequency. When the probability is zero, essentially it's something that happens once and never repeats, or happens so infrequently that it just vanishes to zero completely. Okay.
I think from my point of view, this argument is a bit inaccurate because we're expressing probability as a limit. So we say as a limit, as n approaches infinity, 1 over n becomes 0.
Yes.
But we know that 1 over 0 is undefined. So we can't actually.
The limit, yes, 1 over 0 is, you can define it, I suppose, in some cases, but what we mean is is the probability. When you say probability is 0, one other way to say that is the probability is less than any positive number. So the probability
Right. So we
is
can
less
say
than
that
any positive.
we can say the probability approaches 0, but we could never say that it's exactly 0. That just bothers me.
The probability is the limit. If of course,
Yes.
it might not make sense if you can argue that the limit does not make sense for various reasons. But if the limit makes sense, then the probability is that limit, right? So because the interval, look at it, because when we cut the interval, your objection is very interesting. But when we cut the interval, you might of course object that intervals are not possible to cut. There are many objections that you can raise,
Right.
right? But essentially, intuitively, the interval can be cut into smaller and smaller chunks. Intuitively, I'm not saying that maybe eventually it's completely nonsensical, but smaller and smaller chunks, and the moment of arrival, if such a thing is even defined, is not dependent on how you cut it. You understand? So basically, when I cut into intervals, I'm just saying that the probability of the delivery person arriving at that very moment is less than the probability corresponding for that interval, less than 1 over n. So it's less than 100, less than 1,000, less than a million, less than 10 million and onwards, right? So it's less than any positive number. And that, if it's less than any positive number, it feels like it should be 0. I mean, what other thing is there, right? If it's less than any positive number, it is 0, exactly 0. Now, whether it makes any sense, naturally, that's a deeper question. Ultimately, nothing makes sense, right? Which, of course, when you finish this class, you would understand it. So you look around yourself, guys. Does anything make sense? Tell me truly. I'm not sure if what is there, but does anything make sense? The answer is no, absolutely none of it. Good. Why not? Well, watch the German video, or not watch the German video. Think about it and ask yourself whatever made sense. So of course, guys, probability could also, if the probability is 1 seems that it's very frequent. You agree? When the ratio is 1, that means this, one way to get a ratio of 1 is that success is always happening. Yes? But another way to get it is through limiting sequence. So again, I gave some example, but I'm not going to go over it. It's a very similar idea. Is that if something has probability 1, it means it happens with extreme frequency, but still could once or twice, fail to happen. Just fails to happen exceedingly rarely, right? So yes, I mean, my examples for that, my personal examples for that are very morbid. So I will keep you from it. There is not a single night where I don't have horrible nightmares. And I love to sleep. It's all of them, of course, but why philosophy 101, right? It's hopefully advanced philosophy since it uses probability. Yes, I majored in philosophy at some point. Yes. All right, and now, guys, the ultimate question for today. Are there situations where probability does not exist? You understand, guys? Probability, when people say probability doesn't exist, obviously it's not the same as probability is equal to 0. Do you understand? Right? Probability not existing, first of all, do you understand what it means for probability not to exist conceptually? Can you picture it? No, if a situation doesn't exist, then success never happens. Do you agree? If you say the probability of seeing a unicorn, you might say, well, you cannot say it doesn't exist, because if you don't see a unicorn, then the detector for unicorns is always going to say 0, 0, 0, 0. So you're never adding up successes. So it's always 0 divided by number of trials. So you get probability equal to 0. Yes. So could something be so strange that it has, or maybe not strange, that it has no probability? If you cannot come up with an example on the spot, you should think at least, would it make sense technically speaking? You understand what I'm asking, guys? You understand that probability, you have to have a very concrete grasp of what it is to even begin operating with it. And of course, as Barry said, and when I think more about it, I just realize I have no idea what I'm talking about. I'm teaching a probability. I just try to pretend better that I know what I'm talking about each time. But truly, probability is mind-boggling. I don't understand what it means. Ultimately, right? If you toss a coin, it feels, at least if to somebody who believes in determinism, it feels like it should always, based on the information, should always be already determined what will happen to it, right? So there should not be two universes, whatnot, right? And what does it mean that they just arise? Yeah, but in terms of the mechanism of the limit, guys, what does it mean about the limit? Remember, so we say that probability is the limit of the ratio of successes to the ratio of trials. The ratio of successes to trials. This limit is the probability. So how can probability fail to exist?
If there were no trials at all.
If there were no trials at all, let me think about your objection. If there are no trials at all, then maybe a computer would say, I'm not sure what a computer would say in that case, because there is no sequence generated, right? But let's see if we can add something to it. That's an interesting one. I have to think about what you said, if it could be viable here. But in some sense, if you don't do any trials, it's like a Russian way of the Russians, there is the lazy Ivan that lies on the stove and keeps warm in the winter and doesn't do anything. I can show you cartoons if you want to see those, right? So that's kind of the Russian ideal. But you want to come up with examples where something is happening. So here is maybe one thing that I could suggest.
I was going to suggest the so-called halting problem in computer science.
Okay, well, interesting. Here you go, right? So something where something is not halting, so there is no conclusion, even though, by the way, limits, when you generate it physically, when you generate the sequence physically, you notice there is already kind of something weird about it, because how do you know, as finite beings, that the sequence will converge? Empirically, if you toss a coin, your first problem, if you define it in terms of sequential, in terms of the limit of a sequence, you have to throw the coin infinitely many times. Not only that, you have to do it infinitely many times. The full experiment, you have to throw the coin infinitely many times through infinitely many trials, and the result is always the same, because the sequence is different every time you begin it anew, right? So I throw the coin infinitely many times, and I see the ratio is exactly 1/2. Then I do it again, and the particular terms of the sequence are different, but yet the limit is the same. How do I know that should be always the case? Maybe with a coin, I already believe I know nature's preference, right? I know nature doesn't care. So if nature doesn't care if it's heads or tails, that should be equal. Heads or tails should approach to be equal. And that's maybe how I cheat my way through it.
Oh, I have another idea. Maybe it's like if there's no successes or failures, like you can't have a success or a failure, since that's
well, that will happen soon with the reform, with school reform. You cannot have success or failure, but for now, usually you still can have success or failure. But interesting idea as well. Maybe there is somebody who wrote it. I'm sorry. Say taking the package example, it would alternate between arriving 1 and not arriving 0 at the same time. So the probability of package itself arriving does not exist. Arriving not, well, I mean, maybe if you, Gustavo, maybe if you phrase it a little bit differently, perhaps it is similar to what I have in mind. So here is at least how I think of it, guys. I'm sorry I hurry you. So imagine that you live in this universe, in this very unpleasant universe, where you're a scientist inside of this device and you have this very special coin, right? And when you toss it, right? When you toss the coin, when the experiment starts, the system, just without you controlling it, something from the outside switches, right? So you have this very interesting coin where you toss it and it always lands heads. You do it, you do experiments, always lands heads. And then you call your friend and say, okay, well, try the experiment. And he does the experiment. And when he does the experiment, it always lands tails. Okay, so on those devices, you have, and then they notice that when they try the experiments, there is a probability of the outcome coming up always heads, or the outcome coming up always tails, but there is no probability of the coin actually landing heads or tails. You understand? So what happens is that with each new experiment, the coin is deterministic, but in the opposite direction. Something is switched about it. That's one way to imagine what can happen. Okay, so it is almost like a device. You can simulate that with a device. It's a weird example, but imagine having this device where you press on, and when you press on, the device randomly flips into state H or into state tail. You understand? The device randomly selects to be in state H or in state tail, and when it's in state H, it's always producing successes heads, and if it's always in state, and if it's in state tail, it's always producing tails. So here is what's happening here. Do you see? The probability that it will be in state H is 1/2. Yes, but the probability that the outcome of the coin is heads does not exist. You understand? Because if you repeat the limit of the sequence, it doesn't converge. Because at times when it's in state H, the limit always converges to 1. And at the times when it's in state tail, the limit converges to 0. You follow? So that shows you, maybe not in the most spectacular way, but it shows you that that there are situations where the probability of success does not exist. There are in real analysis more concrete examples that of non-measurable sets where where you can see that the probability doesn't exist in a mathematical sense for a non-constructed example. So there is such a thing in mathematics, in real analysis, it's called non-measurable set. In other words, let's say something that does not have area, right? So you can define what you mean precisely by area, and there are objects out there in mathematics that do not have area. So objects in the two-dimensional plane, but they don't have area. Isn't it interesting, right? So those are known as non-measurable sets. So probability is very directly related to the concept of area. And the idea of probability not existing for certain events is equal to certain objects in space, in two-dimensional space, not having area. Well, counter set is related to that. You can use a counter set to a sort of counter set has area 0. I should say this, right? Counter set has area 0. You can create modifications of it by a function that will make it have no area. Good. So I hope, guys, you understood several things. I hope you understood what it is that what is probability, and yes, and that we think of it right now as a sequence. Yes, if you want to stay, guys, somebody asked me about the exponential function, right? E to the x and the development of that, and maybe some sort of thing relating it to physics. If you want to talk about e to the x or some other things that you are bothered by, then stay after class. I think we are done, right, for today. And I will let you go. Yes. Goodbye. If you want to stay, then stay. If not, goodbye, guys. See you later.